Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of particle physics with the course code PHY 452, we are at the lecture number 19 and the topic is collisions. Collision is a very important tool in particle physics where we not only use them to find out the new particles or to discover the new particles, but we also use them to find out the structure of the composite particles. For example, in LHC, that is Large Hadron Collider at CERN, recently the two proton beams were accelerated and then collided, and after their collisions they break apart into their constituent particles and the Higgs particle was discovered. Therefore, these collisions are very important to understand. And we also know that when we make the particles to collide, we first accelerate them so that we can get higher energies, and when we accelerate them they become relativistic, and these collisions are relativistic collisions. So therefore in today's lecture we will develop the relativistic collisions framework for colliding different particles. So let's start first with defining proper time and proper velocity and also then proper momentum. What is proper time? You know that in special theory of relativity we have two frame of references, two inertial frame of references where the measurement in one frame of reference is converted into the another frame of reference with the help of Lorentz transformations. And then one is wondering that what is the time or velocity or other quantities in one own frame of reference defined. So in our own frame of reference, the time which we are measuring is called the proper time. For example, over here you can see on the left side this d tau. So this is the time interval for the proper time, and this dt is the time interval in another frame of reference, and gamma is the Lorentz factor. So one always is measuring, an observer is always measuring the interval d tau in its own frame of reference. But the same interval when measured from the different frame of reference is dt. So there is coming the notion of proper time, which means that the time interval or time in one's own frame of reference. And from this we also define the velocity. This is actually the usual velocity, which is defined as the change of position divided by the change in time, and this is the normal time, that is dx by dt. But we can use this to define the proper velocity. We use the symbol eta over here for the definition of proper velocity, and you can see from here that it is dx by d tau as compared to the usual velocity, which is dx by dt. So dx by d tau is called the proper velocity, and it is the velocity of when observer measures velocity of some other particle or some other thing, object in its own frame of reference, then we say that it is proper velocity, because velocity does change from one frame of reference to another frame of reference. And then this proper velocity is related to the usual velocity by this Lorentz factor gamma, as these time intervals were related. Similarly, the velocities are related by the to the usual velocity with the Lorentz factor gamma. So after the these definitions of proper velocity and proper time, we develop the 4-vector notation for the proper velocity. You can see this eta mu. So this eta mu will have not only the space component but also the time component, and you will see in a moment that time component will be the speed of light. So eta mu, as you know, it will be 4 component. Mu goes from 0 to 3. So 0 component is the time component, and 1, 2, 3 are the space components. And if we plug in here these values, you can see that for the 0 t when mu is 0, this is eta 0 and dx 0 by deta. But dx 0, we, as in the previous lecture, has developed that x0 is the time component and it is equal to ct, where c is the speed of light and t is the normal time, or the time measured in another frame of reference. So and we also change this d to the t dt, and as on the previous slide we have learned that theta is equal to 1 over gamma dt. So if we put these values over here and do the calculations, you find out that this is equal to gamma c. So as I told you, the time component of the proper velocity is equal to the speed of light multiplied by gamma. So it depends upon gamma, but it is multiplied with the c. Okay. So in 4 vector notation, this eta is equal to gamma. This is the time component and the rest of the space components. And next thing which we can do is to calculate the this invariant, that is eta mu. This is the square of the velocities, and when we calculate this, you can see that in the time component part we will have gamma square c square, and then minus v square and vy square and vz square, vx square minus vy square vz square. These are the 3 components of the usual velocity, and this is the time component which gives us the speed of light square. And then you can take the c square common outside of this bracket, and we will have 1 here and 1 minus v square c square. And when you put the value of gamma over here, this is exactly the reciprocal of the gamma, and with it, gamma square actually, and it will get cancelled out with the gamma square, and we will be left with the c square term over here. So you see that the square of the eta or construct this invariant which is constant, that is speed of light square c square, and this is manifestly invariant because it is a scalar quantity, and then we know it is manifestly invariant under Lorentz transformation. Okay, next we turn to the another basic definition, and that is of momentum. So momentum is defined as, the relativistic momentum is defined as mass multiplied with the relativistic velocity eta, or the proper velocity eta. So in this way you can say that this is the proper momentum because it comes from the mass multiplication with the proper velocity. You know that the momentum definition is product of mass and velocity. So in this case the velocity is not the usual velocity, but it's the proper velocity. Therefore it is you can say that it's a proper momentum. And the similar equation, the same equation can be written in the 4 vector notation. In 4 vector notation we have p mu m eta mu, and now it is interesting to know that what will be the time component of this momentum, and you will see in a moment that we can turn this time component of the momentum into energy. And how we do this? So let's do a simple calculation. First of all, this is the space component, special component of momentum only, and here you can see mass multiplied with velocity, although it is a relativistic one because you see the gamma factor over here, 1 over 1 minus v square by c square, but it's the special component of the momentum, for momentum. And the time component p0, you can see it's gamma mc, and it is the time component of the momentum. So in this way you have seen that we have constructed the proper momentum with the help of this new velocity, proper velocity eta, and this is the 4 vector notation for this momentum. And then we can see its space component or a special component and the time component both. Okay, so after this we move towards another important quantity called energy, and we will use all these quantities defining now in later into the collisions definition. So energy is a very famous equation connected to the mass, that is E is equal to gamma mc square, where gamma is the Lorentz factor and its value is 1 over 1 minus v square under the root, and this is mc square. So this is the relativistic mass energy relationship, where you see that mass can be converted into the energy, and it is now relativistic definition. So we are making everything relativistic, so time, velocity and all these things, and energy. And in the 4 vector notation, if you want to write out, excuse me, and 4 vector notation, then we know that the p mu was E by C, as I mentioned in previous slide, that the 4 vector p mu, the time component, can be written in terms of the energy, and you can test it over here that it is really the momentum, because if you put the value of E over here, it is mc square or gamma mc square, and 1c will be cancelled and you are left with product of mass and velocity. So this is the relativistic, or you can say the time component gives you the relativistic momentum. By relativistic I say the product of mass with the speed of light, and then the special components px and py and pz are the usual ones, but in the time component, or in the first component, zeroth component, you can have energy inside the momentum, as we had speed inside the x. If you remember, we had the speed when we defined the coordinates. The time component of the coordinates had speed of light over here. Similarly, the time component of the momentum has energy defined over here. So this is a 4 vector notation for the momentum, but in the time component you see the energy. And we can also calculate the invariant, the momentum invariant, which is p mu, and this is easily can be calculated by taking the square of it. So this will be E square by C square minus P square, but this is equal to m square C square, because if you multiply it with C square and do this calculation, you will get m square C square equal to this. So this is manifestly invariant. So what do we mean by manifestly invariance? By manifestly invariant, we mean that it is a scalar quantity, and under Lorentz transformation, without calculation, just by looking at it, we know that it will not change under the Lorentz transformation, and we call it a manifestly invariant, because this m is constant, c is constant, so they have no indices, and we know that under the Lorentz transformation these are not vectors, these are just the scalars or even numbers, so it will not, their value will not change when we go from one frame of reference to another frame of reference. So in this sense we call them manifestly invariant. So this quantity p mu and p mu is a manifestly invariant quantity. Okay, after defining this energy in terms of the 4 vector, now here you might have noticed that mc square by 1 minus v square by c square factor coming from the gamma factor. So what we can do now, that take this 1 minus v square c square upstairs with the power minus 1 by 2 for this under root, and then we can expand it into power series, or the Taylor expansion. That's very interesting point. Because if energy is expanded, and you will get in the leading term mc square, and the second term is known to you, this is the kinetic energy term, 1 over mv square, and this is the other terms are also kinetic energy terms, but these are not common to us, because these are the higher order contributions coming from the higher power of the velocities. But now we can separate them into 2 parts, and the first part in the limit. So if we go to the limit, in order to understand this expansion of the energy, if we go to the limit when velocity is very, very smaller than c, then we can see that this first term is actually the rest mass energy, because when particle is at the rest, then this mc square is its rest mass energy. If you forget about these contributions, higher order contributions, then E is equal to mc square. You know, this is that energy which is giving us this is that energy which is coming from the mass of the particle. For example, in case of photon, the rest mass energy is 0, because when photon comes to rest, it has no mass, and therefore its rest mass energy is 0. But for electron, this rest mass energy is not equal to 0, because it has some mass when it is at the rest, and it is equal to its mass. But when it moves, it gets further energy coming from the kinetic energy and converted in the kinetic energy, so its energy is greater than its rest mass energy. And these rest of the terms are actually the relativistic kinetic energy terms. This first, as I already mentioned, this first term is well known to you, and the second term is also the relativistic kinetic energy. So you now know that this energy is sum of the rest mass energy and the relativistic kinetic energy. And this rest mass energy is coming into the leading order because V is raised to power 0 here, that is 1, and when you calculate the velocity square and so on. And from here you can also know that when V is very, very smaller than C, then you can ignore about you can ignore the relativistic corrections over here. Okay, this was the Taylor expansion, and it was telling us about the energy. Now we move towards our main topic, that is collisions. And we will discuss these collisions in both cases, that is the relativistic collisions and the non-relativistic collisions. And why I am telling you the non-relativistic collisions, because these are also important for comparison's sake, because different relativistic collisions could be understood if we know the non-relativistic collisions, and these collisions you have learned in school physics, so this will help you to understand relativistic collisions. So we have already defined all the parameters, quantities needed to define relativistic collisions. So now we will also make one comparison between non-relativistic and relativistic collision, and this will give us an easy way to understand relativistic collisions. Okay, let's start with the non-relativistic collisions. First of all, the properties of these non-relativistic collision, and a very important property is the conservation of mass. So if we have two particles colliding, for example particle A and particle B, let's say the particle A is coming from here and particle B is coming from here, and they collide over here. So the total mass, the sum of their masses, that is MA plus MB, if these particles somehow changes to other particles, these particles, so this is particle A, particle B, and this is C and D after the collision. These are the after the collision, these are the before collisions, but the total mass before collision and after collision remains the same. This is called the law of conservation of mass, that mass cannot change. Or maybe that particle A loses some mass and particle B gains some mass, or other way around, and particle C is constructed and particle D is came into being with different masses. So masses of the particles, individual particles can change, but the total mass on before collision and after collision cannot change. In non-relativistic collision, and as well as we will see in the relativistic collisions, that the total mass before and after collision remains the same. And then the momentum is also conserved, that the total momentum before collision, PA and PB, although the momentum of the individual particles can change, but the total momentum of the system cannot change. So PA plus PB must be equal to PC plus PD. And kinetic energy, third thing is kinetic energy. Kinetic energy may or may not be conserved. There are two types actually collisions in non-relativistic. One is the first one is where the kinetic energy remains conserved, and the other one is kinetic energy is not conserved. So both types of collisions are possible. Now we go to the types of non-relativistic collisions. In non-relativistic collisions, similar types can be defined. For example, the first type is the sticky collisions. What do we mean by sticky collision? This means that if two particles are coming closer, and when they collide, they just stick to each other and form a bound state, kind of bound state. This we call a sticky collision. In these sticky collisions, the kinetic energy decreases. The kinetic energy before and after collision. So you can see that this is the TA kinetic energy of particle A before collision, and this is TB, the kinetic energy of particle B after collision, and together this total kinetic energy is greater than the kinetic energy of particle C, which was created after the collision, plus the kinetic energy of particle D, which was also created after the collision. So the total energy before collision and after collision is not same and this is greater than this. In this is called that kinetic energy was decreased. It was greater before the collision but less after collision, and we call it the sticky collision. And then we have an explosive collision. What do we mean by explosive collision? In this case, the kinetic energy increases. That is, the kinetic energy before collision of this system is less than the kinetic energy after collision. Such kind of collisions are called explosive in a sense that the particles created are moving with the higher velocities. That's why they have higher kinetic energies. So higher velocities, so a kind of explosion is done, though all the components were less moving, but now they are moving with the higher velocities and some sorts of explosion is there. That's why we call it explosive collision. And the third one is the elastic collision, where kinetic energy is conserved. So on the last slide we discussed that there are two types of collision when kinetic energy is conserved and kinetic energy is not conserved. So when the total kinetic energy before collision is equal to the total kinetic energy after collision, we say that the kinetic energy is conserved and we call it elastic collision. But if this is not the case, the first case A and B, we call it the inelastic collisions. Okay, so after giving you the types of the non-relativistic collisions, it is time to give you the types of the relativistic collisions as well. In this case, in relativistic collisions, we also have sticky collisions, but the definition is slightly different. For example, kinetic energy decreases and rest energy and mass increases. Because kinetic energy is in the sticky collision where the two particles form a lump, the kinetic energy decreases and rest energy and mass both increase, because this kinetic energy is going into their rest energy and mass. And on the other hand, if we have explosive collision, we have kinetic energy increases but rest and mass are decreases, because in relativistic collisions energy and mass is the same thing, and one can convert from energy to mass and also from mass to energy with the help of equation E is equal to mc square. And the third one is the elastic collision, where kinetic energy, rest energy and mass are all conserved. So we have all these four quantities conserved with us, three quantities, that is kinetic energy before collision and rest energy before collision and mass before collision are just the same as kinetic energy after collision, rest energy after collision and mass after collision. Okay, so in relativistic collision, these laws are also obeyed, that is the law of conservation of energy and momentum. So we see that energy is conserved, that is the total energy before collision of the particle A and B, and after collision the new particles born E and C, but the total energy is conserved. And this is a very important law of conservation of energy. It is not violated in the relativistic collisions. It is actually never violated. And similarly, we can also have the momentum conservation. So the total momentum before collision and the total momentum after collision is just the same. So the two particles having momentum over here and here is just the same. And we can also write it in form of the 4-vector notation, where P mu A plus P mu B, that is the 4-vector before collision, the total, so it also has energy in there. And so the total 4 momentum before collision and after collision is same. So law of conservation of energy and mass both are intact in relativistic collisions. And the last property is the kinetic energy may or may not be conserved. As you know, it can be conserved. We have elastic collisions, and it may not be conserved. Then we have inelastic collisions. So all these collisions are possible. Now we at the end turn to an example, and this example is that if we have two lumps of clay, so very simple example, just to give you an idea that how one can use these collisions, and each of mass m. So let's say we have just two clumps of clay, not particle, just clays, but you can extend these calculations to particles in different scenarios, and I will give them in exercises to help you understand these concepts better. I will give you an many examples and exercise where you can calculate the different properties in the collision. So each of mass m have an head-on collision at this velocity 3/5c, and they stick together because it's a sticky collision and form a bound state. And what we want to know is what is the mass m of the final composite lump. So the two particles are coming and both having the same mass, this small m over here, and they just collide head-on this very high velocity 3/5c, and they stick together. And the question is, what is the mass m of the final composite lump? And the answer is, first of all, we have to check for the conservation of energy, which says that E1 plus E2 is equal to EM. These are the two particles before collision. That is one of the mass m, E1 is the energy of the first particle and E2 is the energy of the second particle. They collided with this speed and they sticked together, and this is the energy of this lump at the end. Okay, so how can we calculate now? We also invoke the law of conservation of momentum over here, which says that the P1, which is the momentum of the first particle, and P2, which is the momentum of the second particle, so that this total momentum before collision must be equal to the total momentum after collision. So we see that both laws are here, the law of conservation of energy and law of conservation of momentum. So we use this mc square equation. Mc square is equal to 2em, and if we put the value of em over here, you can see, and also the velocity v by c, and make this simple calculation, then you know that we have determined the mass of this lump. Okay, so in this lecture we have talked about in detail the process of collisions, and as I have told you, in modern particle physics and also in old days, these collisions were used to not only discover the new particles but also to understand the properties of the matter, and these are very helpful. So what we do that we accelerate the particles and then we collide them. So different types of particles collision are possible. So for example, in this modern era, in Large Hadron Collider, which is at the sun, there are two beams of protons are accelerated and then collided, and after the collision, when they collide at such a high velocities and kinetic energies, they actually break apart into their constituent particles. And then there are a huge mechanism developed to study their constituent particles or these debris, and by this way we were able to discover the Higgs particle because it exists at a very high energy, that is 125 GeV. It's not very high, but it was hidden there. We couldn't see it because it lives for a very, very short time. So the only way to see it was to collide protons, because we believed that protons or quarks are made of there is another particle Higgs. So the only way to see it is to make a collision, and after that collision this particle was created but then decayed very quickly, but from the decay product it was possible to know that there was a Higgs particle. So by the purpose of this to tell you was that these collisions are very important tool, not only in your basic understanding but also for the research purpose. These collisions provide us a very important tool, and we use them to probe the matter inside and find out what is the structure of the matter and what if there are new particles are there. So with this I say thank you.